let's start. Any questions from the last class? So we basically wrapped up our discussion on various bounds on the size of codes, particularly for asymptotic block size. We saw that there are both upper and lower bounds known on the size of error correcting codes with a certain minimum distance, but ultimately there is still this gap. We don't really know what is the maximum achievable rate for a given minimum distance. Right, so the best known lower bound, at least what we've seen so far, is the JV bound, and the best known upper bound is the LP bound. We didn't really discuss the LP bound in too much detail, but I basically gave you the idea of how one can construct a low, or one can obtain a lower bound by formulating the problem as a linear program. And we saw a bunch of other bounds: the Hamming bound, the Singleton bound, the Plotkin bound, and the LIS bound, which at least for asymptotically large n and binary field size, it is not these are not optimal. These are looser than the LP bound. But in many cases, particularly for small n and for various field sizes, some of them can be better than the others. Right, so depending on the n and depending on the q that you have, you generally try out one of these bounds, find out what is the best bound achievable, and in case you can design a code which achieves that bound, then you know that you can't do any better. That gives the absolute best that you can possibly hope for. Okay, so we'll see a bunch of codes which actually meet some of these bounds. So in particular, the Reed-Solomon codes, as I mentioned, correspond to the max. They are essentially maximum distance separable, or they achieve the singleton bound. Okay? But unfortunately, they require, as we'll see later, they require a huge field size. Now again, so we've seen a bunch of different techniques for deriving upper and lower bound. And now what we want to do is actually be able to construct codes. Right? We want codes which achieve at least some of these bounds, and we need a means of efficiently encoding and decoding them. So for that, we'll first discuss a little bit of algebra, and then proceed to design these codes, particularly the class of Reed-Solomon codes and so on. And we'll see that they have a very nice algebraic structure, which helps us, which is basically used to design good algorithms. Okay. So any questions? All right. So maybe before I start with that part, any questions regarding the assignment? What was the assignment? Easy, difficult, moderate? The last. Okay, so the last question. What was the question? Huh? Okay. So I guess you're given an NKD linear code, and you have to design an efficient decoding algorithm. Right? Anyone got this? Okay. So what was the decoding complexity that I? So fine. So what kind of algorithms do you know which run in NQ? Okay. Correct. So what algorithms do you know that run in order n cubed? Like basic algorithms, not necessarily related to error correcting codes, but in general. Yeah. Yeah, just give me some algorithms that you know. Yeah, any problem. Okay, what about matrix inversion? How do you do matrix inversion? Okay, that's again horrible approach. So what is the other way you know to invert a matrix, or basically solve a system of linear equations? Gaussian elimination, right? Okay, so let's try to see if that can be done. So what are we given? We're given a code C, which is an N A D linear code, and we know that whatever d minus 1 location, at most d minus 1 locations have been erased. And from this, our goal is to recover the actual transmitted code word. If we can recover the code word, then we can recover the message. Okay, so let's try to recover the transmitted code word given the received vector. So suppose that x is the transmitted code word. You receive a particular y, which is obtained by erasing some particular locations of x. So without loss of generality, I will assume that y is basically the row vector. So let's assume that the first d minus 1 locations have been erased. It doesn't really matter, but notationally it will be more convenient. So I get erasure, 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 erasure. The first d minus 1 locations are erasures. Then I have xd, xd plus 1 and so on up to x. So this is what I have received. Okay. So what do I know about code word? So the code word should satisfy some system of linear equation, right? One way is to write it using the generator matrix. So it is some u times g. But really at the decoder side, you should be thinking of it from the parity check view. So you know that h times x is equal to 0, or hx transpose is equal to 0. So let's see if this can be used. So what do I know? I have to somehow be able to recover these symbols. I know these symbols. Okay. So let me write h as two submatrices. One is HE and HE complement. So these are basically the columns corresponding to the locations that have been erased, and the remaining are the columns which correspond to those locations which have not been erased. So in this particular example, these are the first d minus 1 columns of H, and the rest of them are the remaining n minus d plus 1 columns of H. Okay. And what are the dimensions of H? N minus k by n meter. Again, it's the same H, I'm just writing it out as two separate submatrices. And I know that this times x, so let me call these locations x erased, and these are x unerased. I know these values, I have to somehow be able to find these values. So x suppose x unerased, I know that this should be equal to 0 vector. Agreed? Okay. Now what is this equal to? It is nothing but HE times x transpose plus H unerased times x erased, and this has to be equal to 0 vector, right? Now this makes things much easier because I know this value, I know H, I know the value of x in the unerased locations, so this is a vector that I know exactly. Let me call this some vector b. This is I want to find these values x array. So h erased x erased transpose is equal to minus. So all this, so finding x erased essentially corresponds to solving this system of linear equations. This has complexity at most order n cube. And space wise, what do I need to store? I only need to store the matrix. I need to just know the parity check matrix. How does the decoder work? So you receive a particular vector, you know d. So if there are more than d minus 1 erasures, then there's nothing you can do. Give up. If there are at most d minus 1 erasures, then you solve the system of linear equations. So firstly, you have to be careful. Why is it true that I can solve this system of linear equations? Remember, given a H is full rank, why? Okay, so what property are you using to claim that this is full rank? Remember, it could be any d minus 1 location. Yeah, correct. I know, but why is it that this system of linear equations has a unique solution? If I have multiple solutions, then I can't recover x exactly, right? But the claim is that as long as there are at most d minus 1 erasures, I can solve the system of linear equations uniquely. And why is that true? What property do you know about the parity check matrix? In terms of the minimum distance? Okay, for this system of linear equations to have a unique solution, what properties does this submatrix HE have to satisfy? It should be full rank. And what will the rank be equal to? No, what are the dimensions of HE? N minus k by d minus 1. And what can you say? So which one is going to be larger, n minus k or d minus 1? Will be larger, right? So what can you say about the rank of HE? How large? So it can be at most d minus 1. Okay? But you're picking an arbitrary set of d minus 1 columns of H. What can you say about this? Is it always going to be full rank? Why? Arbitrary set of columns. But any set of d minus 1 columns can be erased, right? It's an adversarial erasure channel. But what property do you know about the parity check matrix? Exactly, right? So for any linear code, every set of d minus 1 columns of H are linearly independent, where d is the minimum distance. Right? So this will always be full rank, and therefore you can correct d minus 1 erasures always. So there's an efficient way of decoding all the way up to the minimum distance minus 1 for an erasure channel in a very efficient manner, polynomial time algorithm. So that's the speciality of erasure channel. They're pretty simple channels to look at, but more often than not, you can construct very efficient encoding and decoding algorithms. That is not the case for, say, the binary, say, bit flip channels. Erasure channels are nice. Any questions? Yeah, so it's basically order n cube is because you have to solve this system of linear equations, and that takes order whatever n minus k cube in the worst case, but k could potentially be, yeah, linear in n. Any other questions? So were you able to solve the puzzle question about the three-player game? How do you do it? Yeah. Okay. So let's hear your solution. So again, remember the problem was the following: you are given whatever 8 by 8 chessboard. In fact, any board which has 8 by 8 tiles, and so there are two people, yes, A and B. So A and B come into the room. A and C are in one party, B is on the other side. So B basically places coins on this chessboard in any fashion he wants. So maybe heads up, tails up, heads, tails, heads, heads, doesn't matter, any arbitrary fashion, and then points at one of these locations, maybe this particular location, to A. So A now basically looks at the entire arrangement on the board. So far he doesn't even touch the board so far. He looks at the board and then after looking at it, flips one particular, he can flip at most one of these coins. So maybe he decides to flip this head and make this a tail. Flips this, makes this a tail. Makes this a tail. And then he walks out. And then C comes into the room, looks at the arrangement, and then magically says that this was the location pointed out by B. Question is, how do you design a scheme? So A and C can initially discuss and agree upon some strategy, but B is the one who controls the how the coins are arranged on the board and which location has to be chosen. Okay? So no matter how the board is arranged, no matter which location B chooses, A and C should somehow succeed. So how do you do this? Which one? Okay. Correct. Correct. Okay. So basically each square, you represent each square using a binary string starting with all zeros, 6 zeros, then 0, 0, 0, 0, 1, and so on. Right? So the binary represent. So you basically number all of these squares 1, 2, 3, 4, whatever, 0, 1, 2, 3 up to 63, and then maybe think of it as the binary representation of. Okay. Then okay. 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 So basically, so initially there's some arrangement. Okay. So think of, okay. So perhaps it's simpler if you look at a 2 by 2 grid. So there are 4 squares. You label them 0, 0, 0, 1, 0, and 1. So let's say that this is head, tail, head, tail. So you look at all the squares which have a head and then take the bitwise XOR of all the numbers corresponding to those. So in this case, it is 0, 0, bitwise XOR with 1, 0, which gives you 1, 0. Something. This is something. Okay. So that you can call this maybe the state of this particular board. Let's call this the current state of the board. This is when B has initially arranged it. Okay. And now B points to one particular location, say 0, 1, say this particular location. Okay, now what do you do? You will subtract what? Okay, so B points to this particular location. So effectively, he says that the cell that I choose is the cell corresponding to 0, 1. Okay, now so you subtract 0, 1 from the initial state. Subtraction is the same as doing addition. So 0, 1, which is 1, 1. Right, what do you do now? So you flip the coin corresponding to 1, 1. Right, so whatever is in this, you just flip it. Yep. Okay, so you will flip. Are you sure? You're going to flip this. Okay, so now it becomes head, 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 tail. Okay, go to the root. Correct. Correct. Okay, on all the heads. But what will he get? But does he? Yeah. So what is the current state of the board now? What is the current state of the board? This is the one that you should flip. Flip this, then basically you will get 0. So now the current state is 0. Correct. So does everyone get the strategy? Okay. Does this work for boards of any size? For example, will it work for a 3 by 3 board? Why? I subtract the correct. So I view each, let's suppose it's 3 by 3. Okay. Let us say that I view each of these. So 0, 1, 2. Right. So let's say that I view this as elements coming from the group Z. Okay. So what is the state? The state is basically the sum of those locations which corresponds to a head. Right. So I'll get some element in Z now. Okay. What is my strategy? So this is the whatever. Let me call this the initial state, which I know is in Z9. You point me to some particular location on the board. Okay. That is going to be something. It's going to be, this is the location that I want. Correct. That's another element of Z9. Okay. Suppose I do this. And now what do I do? So I basically want to switch somehow such that this now becomes the new state becomes equal to H. Question is, can this be done or not? It should be done always. Correct? Correct. But what does flipping one particular location correspond? The resultant could be, you keep a head at 0 and 8. Okay, so let's say this is okay. No, the state will now be 1 plus 8, which is 9. Modulo 9 is 0. Okay, so that's the current state. Okay. Now, okay. So that will be the current state. Okay. Fine. Okay. And in this case, this case is in fact maybe easier. So you point me to one particular location. Okay. Now what do you think I should do? I want the new state to be equal to 3. Correct. Yeah. But remember, I'm allowed to only flip one of them. So maybe I make this a head. Now what is the current state of the board? It's equal to 3, right? As desired. Great. So but now what can potentially happen? Suppose I want the state to be equal to, let us say, 8. Okay. I want the state to be equal. Okay, maybe 8 is also related. Maybe I might need more. Okay. So let's try to reason this out. What do I have? I have whatever, 1, 2. So all of these are distinct elements. So the current state, or the initial state, is some sum of distinct elements of this particular group. Correct? So okay, so that's the sum. So it's a sum of distinct elements. So in this case, it would be whatever, 1 plus 3 plus 8. That's the initial state. Now what do I want? I want the new state. The question is, can I go from this initial state to this, to any new state by flipping, right? So what does the flip operation correspond to? So either add another element which is not present in this, or you basically subtract this particular element. You're not allowed to do anything more. Okay. Which one? Yeah. Remember, ultimately, it still has to be a sum of distinct elements of the more nothing. So the question is, can you always do that? So, for example, suppose that my new state is such that to get to the new state, I have to add some element which is already present in this sum. I cannot do that. That is not allowed. Right? Suppose that it is 1 plus 3 plus 8, and to get to the new state, I have to add another 8. That cannot be done, right? Because that's not a valid operation. The only valid operation is I add something which is not present, or I subtract this, but that is it. I mean, flipping 0 or not makes absolutely no difference, right? Because the state does not change. So there's really no need to keep 0 at all. Sorry? Yeah, you could be pointing at anything. So it's not easy to see, but requires a proof. The nicer feature about this case, about groups of the size 2 to the n, is that subtraction is the same as addition, right? So basically, flipping corresponds to both addition and it also corresponds to subtraction. So I can add any element I want by flipping. That is not the case over here. So in this case, if I have to add 8 to this, that does not correspond to a flip of 8. Right? If 8 already has a hedge. Right? But on the other hand, for groups of the size 2 to the n, flipping just corresponds to adding that particular number. So, okay, I'll leave it to you as a homework to think about whether this is not possible or this is possible or not for groups in general. Take something smaller, maybe a group of size 5. Okay, and see if you can go from any initial state to any final state or not. Any questions? Okay, so let's start with next topic. This is a little bit of algebra. So what we want to understand is what exactly is the structure of a field. Suppose now I'm given some modulation alphabet, and my goal is to design an error correcting code over this particular alphabet. Now, the exact structure of the alphabet in some cases may not be so important, but the size of the modulation alphabet is certainly important. If someone gives me a modulation alphabet of size 7 or 8 or 10 or 12, I should be able to design an error correcting code over an alphabet of size, say 10 or 12 or 8 or 7. Right? So the question is, in order to be able to construct an error correcting code, I need a field of that particular size because I have to be able to do arithmetic. So far, we've seen that say ZP is forms a field under modulo P addition as long as P is a prime. If P is not a prime, then it's not a field. So does it mean that there don't exist any fields of size say 8 or 16 or 10? So for what alphabet sizes can we construct a field? That's basically the question that we want to answer. And also, given a particular field, how do you, is there a more efficient way of adding, subtracting, multiplying, and dividing? So the field of integers modulo p, where p is a prime, is something that we're all familiar with. We know exactly how to work. But for more complicated fields, I mean, so one way of completely representing arithmetic operations on fields is to maintain a table, right? So if it is this element and this element, then the addition gives you this particular element. So you maintain field size by field size table for both, one for multiplication, one for addition, and every time you want to add or multiply two numbers, you basically do a lookup on this particular table. That's one way of doing it, right? But that's not a very efficient way of doing it, because you have to go through this table every single time. So is there a specific structure for adding and multiplying elements in any arbitrary field? That's the question that we want to answer. So let's start with some of the basics. So even before going to a field, uh, we'll look at a more basic structure, which is a group. So recall that any set G on empty and an associated binary operation plus, which takes two elements of G and puts another element of G, is a group if the following properties are satisfied. Firstly, it has to be associative. So it doesn't matter, the order of addition does not matter. Right. Secondly, there exists an identity element. There exists some element E in the group, which is the identity. Such that E x and thirdly, for every element there exists an additive inverse. We call this x bar. So this is equal to the identity. So these are the three properties that any group must satisfy. Now, in addition, so know that, also remember, I mean, keep in mind what I have not included in this. So I have not mentioned anything about commutativity yet. So a group may or may not be commutative. So even if the addition operation does not satisfy commutativity, it is still a group, but it's a non-commutative group. So in addition, if addition is also commutative, then we call it a commutative group, or sometimes called an abelian group. So can you give me some examples of groups? of integers under what operation? Addition operation. So this forms a group. Okay. Real numbers form a field. I want examples of groups which are not fields. Yeah. Okay, can you give me an example which is not a group? Okay, set of natural and why? Set of natural numbers don't form. Okay, so can you give me an example of okay, so this is an example of a group which is not a field. This is an example which is not a group, but both of them are commutative. Can you give me an example of a non-commutative group? Yeah, set of all matrices. Okay, and what is the operation? Multiplication. Set of all square matrices under matrix multiplication. Sorry? Remove the set of rotated y. Every square matrix invertible. Whatever, there's some binary operation which you call the addition operation. Yeah. So that's a multiplicative group, sometimes called a multiplicative. Yeah. So in principle, I should not call this operation the addition operation. Just that in many cases, when you also have a multiplication operation, it makes it convenient to call this the addition operation. This is just a binary operation. So a better notation would have been to call this some star. Okay, the set of all full rank matrices. Invertible n by matrices under matrix multiplication. Is everyone convinced that this is a group? So its matrix multiplication is associative, so there's no issue over there. Identity, it is the identity matrix, and every matrix is invertible, so an inverse always exists. And it is matrix multiplication in general is not commutative. Okay, and going back to that point that you made earlier, what about the set of all rotation matrices? What can you say about it? Yeah, do they form a group? Correct. Correct. They form a commutative group. So the set of all invertible matrices forms a non-abelian group, a non-commutative group, but within it there is a commutative group. It is a set of all rotation matrices. Okay. So now let's look at some properties of. Remember that we are starting with a set of very basic properties. And so many of the things that we take for granted are not necessarily true. For example, all we know that there exists an identity, but given a group, can there be two different identity elements? For a given element, can there be multiple inverses? Is it possible or not? So it turns out that that's not possible. So for any group G, the identity is unique. Okay. So let's suppose that E and E prime are identity elements. Again, we should only use the properties that we know in order to prove this. So let us take E. Okay. I know that E prime is an identity element. So I need to show, so I should use only these three properties to come to the conclusion that E is equal to E prime. If E and E prime are identity elements, I want to show that E equal to E prime. That will confirm that the identity element is unique. There can't be two distinct identity elements. So let us take E. I know that E prime is an identity element. So what can I say? E is equal to E plus E prime. Correct? But what do I know about E itself? It is an identity element. So what can you say about E plus E prime? It's equal to E. So E equal to, it seems like a very trivial statement, something very simple, but you still need to formally argue that E is equal to E. You can't have more than one identity. So here, so that is why it is important to say that x plus E is equal to E plus x equal to x, right? Because in this case, we've used the fact that x plus E prime is equal to x, right? So this is sort of addition from the right. But on the other hand, in the second step, we use the fact that E plus x equal to x, addition from the left. So this may not be so important when the group is commutative, but in a non-commutative group, both these statements are required. You can't just say that x plus E equal to x. In principle, you could have defined a right identity and a left identity which could be different, in which case you can't argue this. So now what we want to argue is that for a given element x, the inverse is unique. Right? Let's say that x bar and x tilde are inverses of x. What I want to show is that x bar equal to x tilde. Now can you come up with an argument? Okay. Ax plus x tilde equal to I. Add x bar on both. Okay. From the left or from the right? From the right. Okay. Guess you want to add from the left. So you're using associativity here. So I mean, this is basically what you're doing. Equal to x bar plus x tilde, which is this is equal to identity. You agree? So I'm going by this formally because ultimately we'll want to see more general fields where the algebraic structure may be very complicated. So we know how to do addition within say integers or real numbers, but things will soon become a little bit more. Okay. Yeah. Right. Do you need to? You don't need to, right? That's what you don't need to. Yeah. Because you want the minimum set of properties which define a group. This would just be redundant. So yeah, that is why this statement of a group does not say that there exists a unique element E. Or this doesn't say for every x there exists a unique x bar in G, because you get that by as a property. We generally do want to keep the minimum set of. So suppose that we have a group G, and let us say that H is a subset G, and H itself is a group. Then we say that H is a subgroup of G. So for example, we look at the set of all invertible matrices and say the set of all rotation matrices, set of all orthogonal matrices, then this forms a subgroup of the set of all invertible matrices. If we take the set of all integers, then can you give me a subgroup of the set of all integers? Yeah, subgroup. Hmm? Plus 2z, 2z itself. Set of all even integers. Addition. It always has to be under the same operation as the group. So the set of all even integers under addition is a subgroup of the set of all integers under it. More generally, you take any positive integer, az, subgroup well, in fact, for any non-zero integer. So given a particular given a particular subset H, how do we check whether it's a subgroup or not? One way is to verify all the properties. You check whether it is associative, whether the identity exists, and the inverse exists for every element. But is there a slightly easier way of checking whether something is a subgroup or not? So, in fact, the following two properties are sufficient to verify that it's a subgroup. Firstly, it has to be closed. A plus B is in H. A, B in H. We don't really have to check associativity, right? Because we get that for free. You know that they're elements of the group, so associativity is directly inherited by the elements. The other property that you require is for every A, inverse exists. So this takes care of property 3, the existence of an inverse. So we're demanding that. The question is now, does for it to be a subgroup, there's one more property which had to be satisfied, right? And that was existence of identity. Does the identity exist in the subgroup? Why? Okay. So E is in G, right? And H is some subset which satisfies these two properties. So to conclude that H is indeed a subgroup, the only property that is not explicitly mentioned over here is that E belongs to H. So every subgroup must satisfy these two properties. Okay? For this to be a subgroup, it has to satisfy those three properties. Associativity comes for free. The inverse always exists, that is this property, property 2. Now I need to show that the identity element is always in H as long as these two properties are satisfied. Right? So can you conclude that identity is in H? Just using these two properties. Exactly. So you know that if A is in H, then A bar is also in H. So this implies from property 1, you know that A plus A bar is in H. But A plus A bar, you know, is the identity. E is in H. And therefore, this is a. So if H is a proper subset of G, then we call it a proper subgroup of G. So if basically H is not equal to G, fit subset of G. Okay. Let us now look at a term that we've seen earlier, the coset. So what is a coset? So let H be a subgroup of G. Okay. And let A be any element of the group G. Then A plus H, which is the set of all A plus H, 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 is called the left coset of H in G, but just omit the in G. And H plus A is called a right coset. And in general, the right coset may or may not be equal to the left coset. If the group is abelian, then the right coset is equal to the corresponding left coset. But if it is non-abelian, then these two may not be the same. Yeah. So just take an example. So take some 2 by 2 matrix. Take, say, the set of all rotation matrices. The left coset is in general not going to be the right coset. Or take some other subgroup. Rotation matrix is any matrix A for which A transpose is equal to A inverse. Yeah. The rotation. Okay. The term rotation matrix is in general used for 2 by 2 matrices. They're orthogonal matrix. Okay, so this is called a left coset, and whereas this is called a right coset. Now the question is, of course, if I give you two different cosets, are they really different or not? Or can there be some elements in common to two different cosets? The other question is, are all the elements of a coset distinct or not? Because I'm adding A to every element of H. Okay? So is it possible that whatever A plus H1 is equal to A plus H2? That's possible. Or another, so basically when I add A to H, does H sort of shrink in size or not? Okay, so basically I'm performing some operation on H. Right? H has a certain size. If H is finite, then that makes sense, but potentially H could even be infinite. Right? Now when I add A to every single element of H, I get a different set. Does this new set, which is the coset, is it the same size as H? Is it bigger or is it smaller? Of course, it can't be any bigger, because after all I'm getting every element by adding some element to every single element, but potentially it could be smaller, right? In principle. So for example, a very pathological example is when, let's say, I take, say, some subset of integers, okay, I multiply 0 to the whole set. What do I get? I get just 0. Right? So multiplication by 0 to any set of integers shrinks the set in size. Goes in number of distinct elements, the size of the set. So it's basically taking a huge set and then you're just collapsing to just one particular. So can something like that happen in a group? The claim is that that doesn't happen. So why do I need this particular property? I need this property because I want to know whether all cosets of a given subgroup, do they have the same size or not? Are there some cosets which are bigger and some cosets which are smaller for a given subgroup? And the claim is that all the elements of a coset are distinct, which must mean that the number of elements in every coset is always the same. So suppose that A plus H1 is equal to A plus H2. In the subgroup. A is any element from the group. So this must imply that H1 is equal to H2 because I can just add minus A or A bar on both sides. So if H1 is not equal to H2, the contrapositive of this says that if H1 is not equal to H2, then A plus H1 cannot be equal to A plus H2. So therefore, there's a one-to-one mapping between the elements of the subgroup H and the elements of any corresponding left coset or right coset. So in particular, if H has finite size, then A plus H also has exactly the same size as H. And the size of any group or subgroup is called the order of that group. So in particular, if H has finite order, then every coset has the same size as the group. Okay, so now that's one property that we need. The second property that we need is the following. So distinct cosets of H are disjoint. So basically, if I take any two cosets, okay, say A plus H and B plus H, right? Either there's no intersection at all between A plus H and B plus H, or they're both exactly the same set. Okay. So let's see what happens. Suppose that A plus H is equal to B plus H. Okay. Or in other words, suppose that there is some non-trivial intersection. So A plus H1 is equal to, so we're looking at A plus H and B plus H. Okay, these are the two distinct, these are the two cosets that we're trying to analyze. So suppose that there is some intersection A plus H1 equal to B plus H2, okay, where H1 2, then A should be equal to B plus H2 minus H1, correct? So A is equal to B plus some H prime. H2 minus H1 is also in H. Okay, so maybe I've called this plus, okay, the inverse, right? So basically I'm adding the inverse of H1 on both sides. So I get A plus H1 plus H1 bar equal to B plus H2 plus H1 bar. H1 plus H1 bar is the identity, so A is equal to this. So A equal to B plus H prime, where H prime is equal to H2 plus H1 bar, which is in sub. Because H1 and H2 are both in H, H1 bar is in H, and therefore H2 plus H1 bar is also in H, just using the properties of the sub. Okay, so suppose that, so we know that this is true. Okay, now let us look at the subgroups, the cosets themselves. So if I look at A plus H, this is equal to B plus H prime plus H, right? Or B plus H prime plus H, correct? But what is H prime plus H for any H prime in the subgroup H? It is H itself. So this is B plus. So they're both exactly the same set. So if there is some non-trivial intersection, then basically they overlap completely. Otherwise, there's no overlap at all. So one thing that we've learned is that the cosets, so if we list all distinct cosets of H, then firstly they have the same size. Secondly, they form a partition of G. They're non-intersecting and their union gives G. Yeah. Yes. H have the same order, same size. They form a partition of G. Okay. Okay. So far it doesn't seem to be something very surprising or non-trivial as yet. You don't really get the weight of this statement so far. But this gives a rather surprising property which is not completely obvious. So now suppose I give you a group. Okay. So consider any G with order some integer n. Okay. What can I say about the subgroups of G? Can they have arbitrary size? H can M be arbitrary? Just be, of course, M has to be less than or equal to N, that is obvious, but can M be any number? It should be, yeah, so basically M should divide N, right? Or N should be some multiple of M. Right? And that is because the cosets of H all have to have the same size and they should form a partition of G. So then M must divide N, and every, yeah, and there are exactly N by M cosets. So in particular, if we look at the group of integers modulo P, if P is a prime, then how many subgroups can this have? Yeah, one, which is which itself, nothing else. In fact, actually two. One is only the zero element. Second is itself. So it can't have any non-trivial subgroup. And we'll make use of these properties later on. Okay. So our goal is to ultimately understand the structure of finite fields, right, and how to construct finite. As it turns out, the way we construct finite fields is using polynomials. Okay. Right now, we know how to do addition and multiplication over the integers, right? And so far we only define addition, and we know what subtraction is. You can always subtract two numbers, correct? So given any number, any other number, subtraction is basically addition with the multiplicative inverse, or with the additive inverse, correct? We know multiplication, but we haven't seen division yet, and that is because so multiplication with the inverse, with the multiplicative inverse, would give you some other element which is not necessarily equal to 1, right? But the set of integers is a little bit special because we can do certain operations which you can't do in every group or every field. There's some more structure to the set of integers. For example, there is an order, right? And there's another algorithm that you've been using since primary school without thinking too much about it, and that is division. So, and division particularly, so given any integers, right, you can always write B as A times Q plus R. So you can write the second integer as the first integer times a quotient plus a remainder, where whatever R is basically, suppose it's a non-negative number or non-negative integer which is less than the absolute value of A. Quotient. Remember, all of these are integers. Now the question is, over what kind of sets can we do something like this? Can we extend this algorithm? This is basically Euclid's division algorithm. Can we extend Euclid's division algorithm to other more abstract groups or fields? So remember, the set of integers does not form a field, correct? It forms a group. So then you can still have some properties of multiplication that are present. You can multiply, but you can't exactly divide. Division of two numbers is not always an integer, right? But in some sense you do, but you still do division over the integers in this particular fashion using Euclid's algorithm. So the set of integers forms what is called a ring. So given a set R, an addition operation and a multiplication operation, we call this a ring if, so firstly, it's an additive group. Okay. And multiplication is associative. There exists a multiplicative identity and multiplication distributes over addition. So A times B plus C equal to AB plus AC. Okay. So let's stop here. I think it's time for the next class. But any other questions in the meantime? So the set of integers forms a ring. And it turns out that for many rings, we can do this division algorithm, Euclid's division algorithm. But not for all rings. So there's something a little more special. Integer ring is special. And in fact, we'll do this for the ring of polynomials.